Hey guys, welcome back to second video in this series on PyTorch. Hopefully from now on the videos will be regular and I apologize for the delay. So today we will talk about a very important aspect of any deep learning framework, which is autograd or automatic differentiation. And this is the thing that makes these frameworks TensorFlow or PyTorch tick. So I will go into how autograd works in some detail and show you a couple of examples. So basically what autograd does is you do not have to keep track of derivatives, and the framework where you will perform computation keeps track of how the derivatives are computed. So basically, whenever you perform a computation, so any computation can be broken down into a series of steps, and any mathematical operation can be broken down into, I think, 10 basic ones, which are like plus, minus, subtract, divide, and the trigonometric operations, and certain others. But then basically anything that you can do computationally can be broken down into those. So as you perform a computation, PyTorch or any other framework generates a computation graph for you. And basically, with the help of this graph, the gradients can be computed because performing or computing gradients is just back traversing in this graph. So using certain, basically certain rules, and that's all. So all you have to do is perform a forward computation, and then the framework takes care of computing the gradients. And as you all know, gradients are the bread and butter of deep learning. So it's good that this mechanism allows you to compute gradients on your own. Otherwise, it would have been a pain to compute gradients. So basically, in the last video, we saw tensors. So tensors are just some kind of NumPy arrays that contain extra information, which is this computation graph or ability to contain computation graph. So yeah, so this is a nice description of how autograd works, and I will post a link to this page. And yeah, pretty much basically you compute. So every time you compute a forward pass or like a computation, PyTorch automatically generates a graph for you, and all you have to do at the end is type the command .backward and it will generate the graph for you. Now, because you are creating this computation graph every time you're performing computation, it might be not very efficient, or both performance wise and memory wise, when you have to just do inference. So for that, PyTorch also provides you the ability to disable computation. So that way you can put your model or your framework or your computation in an evaluation mode, and this extra process of generating this graph is not done. So these are the few things that I will go over, and I will post a link to this page. It is fantastic, and it also goes into the details about how to do multi-threaded autograd and all sorts of cool complex things. So, all right, let me jump into some code. All right, so here I have my VS Code session open with a new notebook. So let's first begin by importing the libraries that we need. So for this, I'll just need Torch, and that I'll import that. Let me see if everything is kosher. Great. Now let's see. So let me create a function, and all this function does is basically creates a tensor. So and let me pass in the value of 3. The dot indicates that it's a floating point value, and then let me also fill an important aspect of this tensor that tells it to require gradients. So if you want gradients in your computation, or if you want to compute gradients of a particular tensor, you need to give this flag requires grad equals true. So that tells PyTorch that you care about the gradients of this tensor. So this is important. Now, what we will do, we will perform a simple computation where I just multiply it by 5 and then take the square. So 5a squared. That's all I'm doing. And then I return both these things. The reason why I created a function will be clear in a bit, but let me start with this. So, all right, so I have this function. And now let me output both these values. So I call this function and I'll print out a, and I'll also print. Oh, one of these days I'll disable IntelliSense because it's getting annoying. All right, so let's see the output. So first of all, the value of a is 3 because that's what I set. And then the output is 5a squared, which is 5 times 3 squared. 3 squared is 9, 9 fives are 45. Great. But you see now for the output, there is a new parameter, the gradient function, which is multiplication backward. So an interesting thing is happening. So for the output, it has this new parameter multiplication backward. I'll come to the details of it. But then this is the function that keeps track of your the backward pass in your computation flow. So this computation 5 times a square has two operations, a multiplication and a square. So, and they occur in certain order. So let's say the power operation occurred first and then the multiplication occurred. So the last operation that occurred is multiplication. So when you go backwards, you would see the multiplication first, and then you will see the power operation first. And of course, these will be the backward versions of those. And that's what this is indicating. I'll go into the details of it, but let's first compute gradients. Let's say you don't care about the graph, you just want to see the gradients. So to compute the gradients in your output function, all you have to do is call the function backward, and it automatically computes the gradients. Now, an important thing is the final value has to be a scalar. In PyTorch, there are ways to go around it where you can convert a non-scalar value to a scalar, but then gradients are always computed with respect to scalars. Um, Otherwise, they will be matrices. And then to get the gradients, I would type a dot grad. So this gives me the gradients. All right, so let's see. So when I run it, I get 30, which is the correct value because if I take the gradient, and a dot grad means it's the, so this particular thing means I am computing dO over dA. So the gradient of is always the function for which I have called the backward, and with respect to is the one that is I'm computing a dot grad of. So great, 30. Why? Because if the derivative of this is 10 times a, and 10 times a is 30. So that's all you need to do to compute gradients. Pretty simple. So no matter how complicated your function is, as long as it's differentiable, all you do is do a backwards to your output and then do print to all the values that you need to compute gradients of. So that's good. Now let me come back to why I created a function. So what's happening here is every time I'm calling this compute, let me call it again, and let me compute gradient again. Eh, Nothing has changed. The reason for that is as soon as I call this compute, I rewrite A and O with a new computation graph. I don't reuse my previous computation graph. I am creating a new computation graph. I'm rewriting. If I didn't do that, let's see what happens. So let me first, again, define A, and then let me perform the computation, and then also the backpropagation. So A is defined here. I define my O, and which is where the computation is performed. And I also compute the backward gradient. Okay, so let me put all of this in one line. So A is defined as 3. Now I compute the gradient. Okay, I get the same value. No harm done, no difference. But what if I execute this bunch of line again? So what's going to happen is I am recomputing the same thing again, and I again compute the backward flow, and then I do a dot grad. Let's see. the value is different. It's now 60, which is 30 times 2. So what's happening? The thing is, if I do it again, I'll get 90. So what happens is here we are reusing that computation graph. So once, even though we have computed the backward pass, now I have a list of all the gradients, but then when I run it again, I accumulate my gradients. I add on to it. So we haven't refreshed our graph. We are using the same graph over and over again without clearing out the gradients. So whenever you perform a computation, it is very important to clear out the gradients. So what clearing out gradients means is setting them to be 0. So you do that by typing a.grad or your variable.grad dot 0. So this makes the gradients that you need to be 0. And now when I run my backward pass, I get the original value again. So this is very vital. Always clear out your gradients after one iteration of computation. All right, great. So now let me get back to this computation graph that I was talking about. So before that, let me pull up an image. Let's see if I can do this on the fly. All right, awesome. Great. Right, so, okay, you can see my cursor. Yeah. Let's look at the forward pass. Okay, so that is the first half of this figure. My input is 3 because the value of a is 3. I first take the square of it, and then so the current value becomes 9, and then I multiply it by 5. And that's my output. So this is the forward operation. Now let's see how the backward operation looks like. So I'll explain what this is later, but when you go back, the first thing you encounter is a backward multiplication. And then you first see a backward multiplication, and then you will see a backward power operation. And then you see a times a. So why is that? Because what's the derivative of 5a squared? It's 10, or rather 5 times 2 times a, right? So this 5 is coming from the multiplication operation. So this 5 is a backward multiplication pass. This 2 is coming from the power operation. So it's a backward power pass. And this a is the original a. So there are 3 ingredients that goes in your backward pass. So while the forward is being computed, you compute that thing. So I start with an input. That's why I get this. When I compute the square, I generate a backward pass graph. So the differential of a power, so 2 to the n, the differential is n times 2n minus 1. So that is what's stored in the backward pass. So here, since n is 2, I just get a times 2 multiplication. So that's what's been stored. Now, when I multiply it by 5, the backward operation is the same as multiply by 5. So I get the same thing. Okay. Now, whenever you start a backward pass, you start with a scalar value, and your value is 1 always. So you start with 1 because let's say you have y. I mean, it's what? Let's say I compute derivative with respect to a. So it's this, and then all the chain rule elements. So finally, you multiply with 1. So you begin with 1. Yeah, I messed this up, so forget this. So you start with 1, you multiply 5, that's the backward pass. So the current value becomes 1, or sorry, 5. 1 times 5 is 5. The backward power operation is just a multiplication by 2, so that becomes 10. And then you multiply by a, which is 10 times 3 is 30. And that is the gradient. So this is a very simple graph. If your graph has multiple branches, you need to accumulate those branches and so on. But this is basically how this computation graph is generated. All right. So when we go back, we first see the multiplication back, and then we see the power back. So, all right, so let me go back and show this to you in code. All right, so how will we see these things? So to see these things, let me again use that function, and I will show you two things. Let me print out what this grad function is. Okay, so for the output, this grad function is a backward multiplication, right? So backward multiplication. What happens if I probe that? So if I do, what's the next function? So first function is multiplication backwards, and the last function, and after that, the next functions is a power backward. Basically, this keeps track of if there are like multiple branches. There are none. So we have a power backward function. So like I said, so first the multiplication backward, then the power backward. Um, let's see how they act. So to see how they act, let me first define a tensor with value 1 to show you the action of them. And then I basically will call, let's say, let me call the multiplication function on temp. It gives 5 because what the multiplication function does is multiply by 5. Let me show you what the power backward does as well. So each function basically takes into account what its previous functions are doing as well. So uh, yeah, so this grad function multiplies by 5. The parv function in because it's the last node, so it also tracks into account the times a factor as well. So if I have to show you that, um, now let me index into the tuple, the first function, and then let me call temp. So it's 6 because it's 2 times 3 because this is the last function, and that's why it keeps track of a as well. So how do I know it's the last function? It's because so if I do next function and then I index into my tuple and then I do dot next function, I see it's accumulate grad. So that means it's the final step. So roughly, I hope I have given you an idea how this autograph is generated. Now you can always construct a visual representation of this graph and so on, but I'll not get into that. But yeah, I hope this was advanced enough to give you an understanding or a flavor of like how to play around with this automatic differentiation. Good. Now, all this while, we have been dealing with scalars. But in neural networks, you have matrices, you have, like a big matrix of weights and so on. How does autograd work? It works exactly the same way, and I'll show you with a small network. So let me first create a network just to be, I just want to make an easy one. So this is my input, has just 3 things. My weight matrix is, let me create a random weight matrix with value. It's a 3 by 2 matrix. And then because we want gradients for the weights and biases, I'll give it the requires grad flag. And similarly, let me create my bias matrix. This would have 2, and this also requires grad. Okay, let me bring this up. All right, and then finally, my final answers. Let me just make it zeros. Or let me make it ones. That's pretty much it. And then my loss, I just define to be, I'll just use an inbuilt function. It doesn't matter what this does. It's basically, I'm just computing binary cross entropy, and it really doesn't matter. It's just some kind of loss. Just don't worry about what it does. So basically, this is my input, which is a vector of 3 entries. I multiplied by weight matrix 3 times 2, and then add a bias, and then finally I have my outputs, and then I compute some loss. So let's run that. I got an error, which is interesting. There is a size mismatch, which is interesting because, oh, oh yeah, I mean, I haven't performed my computation. So I have to do torch.matmul, that's funny, plus b. And this I'll replace with c. All right, good. I've computed my loss, and we can also print that out, some value. So now to get my gradient so now I want my gradient with respect, so gradient of loss, so dl divided by dw, which is the weights, or dl over db, which is the biases. So my gradient of element is loss, so I do a backward on it, and then let me print out the gradients for w, and let me print out the gradients for bias. Great, that's it. So because it's a 3x2 element, that's why I get a 3x2 matrix with the gradients for each element, same for the biases. So for non-scalar values, it works the same way. Okay, so this was all about gradients. What if I don't care about gradients? What if I don't need gradients? So there are, I think PyTorch provides multiple ways of doing it. Let me mention some of the ways. Because if you do not need gradients, that means your computation will be a bit quicker because you're not tracking this computation graphs, you're not tracking the backward passes, so less memory, more efficient. So for inference, when you want to run your networks, not train it, always use no grad mode. So this is done by something called no grad mode. And let me demonstrate this with the same network. So um, right now, when I perform this computation and I query this flag requires grad, which basically queries whether gradient is required, it'll be true because I haven't done anything. So it requires gradient. But what I can do, I can perform my computation in this mode, no grad. So this disables any gradient computation in this bracket. So we go ahead and then basically I paste the same thing here again. What happened? Yep. All right. So let me now print that out. Gradient computation is disabled. Awesome. So that's all you have to do to disable computations. Just so whenever you don't want to perform any gradient computations, just do them in this no grad bracket. That's one way to do it. The other way to do it is, let me grab this. Well, this is not a way to do it, but then let me type it out and then all right, so ooh, that is interesting. Huh. I actually do not know what just happened. Let's see. So what I'm trying to do is, what detach command does is, so when a computation graph is computed, what it does is it just detaches the node from the graph. And then, so since it's detached, it doesn't contain any history of the gradients, and you can just work with it without worrying about the gradients. Let me see what the error is about. Oh, it seems like my VS Code crashed because if I do anything, so let me restart my session. So give it a bit. That is interesting. So let's me a minute while I restart my notebook. All right, so I think the error was due to outdated language server, and I think it should work now. So let's go back. All right, yeah. So where were we? We were here. Let me disable all this crap. And that was a waste of time. I detach it, and then okay, it worked as expected because what I did was basically detach the node from the computation, and then now you can use it to compute whatever. But this is a more performant approach because from the beginning you're not computing any graph. So these are two ways to do it. Another way is if you have a model, torch.nn.model, you can put it in evaluation mode. So that will automatically disable gradient computation. So, so these are some ways to disable gradient computation. Now, I didn't mention how to compute gradients for models, but they also work in the same way. All you need to do is once you have a model, all you need to do is whatever your final loss is, do a backward on it, and then to compute the gradients, you can access the weights of your model with model.parameters method. So this pretty much covers everything that I wanted to talk about gradients. I will upload this notebook with the figure that I drew on my GitHub repo. The link for it will be down below. Also, PyTorch has some excellent documentation on autograd mechanism and also some detailed. Um, so their API is pretty detailed. It's well documented. If you need higher order derivatives, it allows you to compute that. If you want complex derivatives, there is a way to compute derivatives of complex numbers and so on. So these are some even more advanced things that maybe you might run into, but I think whatever I talked about is more than enough for everything that you'll need in your daily life. So thanks for watching, and I'll be back next time with some torch.nn stuff. All right, see you guys.